All right, welcome to Chapter 22, Lecture 2, where we continue our discussion of electrophilic aromatic substitution reactions. So by the end of this video, you should be able to draw the mechanisms of Friedel-Crafts acylation that is different than the alkylation that we learned about on Friday. You should be able to draw the mechanism of bromination as well as nitration reactions. The unifying feature of these reactions is that they are electrophilic aromatic substitutions. So there's a lot of conceptual similarity, but the products are quite different. Once you've learned one, you've learned the others. Secondly, you should be able to predict the selectivity of these reactions based on the aromatic ring substitution. Again, this is something we covered on Friday. We're going to go through these reactions again and talk about how resonance effects can induce various selectivity in the substitution reaction. All right, so just as a review and warm up for this video, on Friday we talked about the activation of an alkyl chloride using a strong Lewis acid catalyst, aluminum trichloride. Give it an La for Lewis acid. This is a trivalent aluminum that has an empty p orbital which can interact with the lone pair on chlorine. Chlorine has 3 lone pairs. It can act as a nucleophile and donate into the aluminum. The aluminum then activates this chloride as a leaving group and helps it leave to generate a potent carbocation electrophile and aluminum tetrachloride counterion. This electrophile, we'll give it the E+ designation when we're identifying electrophile and nucleophile, reacts with our nucleophile partner, the arene. This results in a de-aromatized intermediate, which then undergoes deprotonation to re-afford the aromatized product. So the description of this reaction, some people like word descriptions. We have alkyl chloride activation to give a carbocation, or if primary, so if it's a primary carbon chloride bond, it's a carbocation, like the aluminum is still associated with it, but it is not a full-on carbocation because those are too unstable. This electrophile then reacts with the aromatic nucleophile. The de-aromatized intermediate then is re-aromatized to regain that aromatic energy and afford the alkylated product. There's a variant of this reaction called the Friedel-Crafts acylation. Acylation, this is an acyl species, is a carbonyl, something like this. I'll put a wiggly line, meaning it could be attached to anything, and this is an acyl species, okay? So when we're acylating things, we're adding a carbonyl with a substituent off of it to that species. The aluminum trichloride can activate the chlorine on this acid chloride and generates what's called an acylium ion. An acylium ion is our electrophile, E+, and the benzene is still our nucleophile. Acylium ions are potent electrophiles, and they'll generate the same de-aromatized carbocation intermediate. This one shown here. This is then deprotonated by something like our aluminum trichloride. Which acts as a base. Again, because this is re-aromatizing, this proton is more acidic. There's a strong driving force for deprotonation, where those electrons fall back down to make the aromatic ring. Okay, and so what you need to know is you need to know that acyl species, halide species can react through Lewis acid activation to give acylium ions. You need to know that this reaction for synthesis. Right? But this reaction, as its name would imply, is extremely similar to the previous example. We can go back up and see that the steps are more or less the same. The only thing that's really changed is the substrate. Here we have an alkyl halide, and if we scroll down, we have an acid chloride, an acyl halide here. So mechanistically, they're nearly identical. The only difference is what our substrate is. And indeed, this is often the case for electrophilic aromatic substitutions, EAS. The main difference between electrophilic aromatic substitutions is how the electrophile is activated. So we'll call this step 0, where we have some electrophile precursor and it undergoes a reaction, usually with a Lewis acid of some sort, to give an electrophile, and we'll just give it uppercase A for activated, or I guess I'll put it in parentheses, activated. All right. And so this is our active electrophile that's a strong enough electrophile to react with arenes. Remember that aromatic groups are quite stable. They need really strong activated electrophiles to react with them. So in this case, the step 0 is really where electrophilic aromatic substitution is differentiated. Once you know this general sequence of steps, you've learned many of the electrophilic aromatic substitutions. And so that's what we're going to talk about for the rest of this video. We're going to talk about two common ones: halogenation, using elemental halogens and Lewis acids, as well as nitration. And again, just to reemphasize, you're not learning 3 separate mechanisms. You're learning 1.3, where the step 0 is slightly different between them, but the ensuing electrophilic attack and proton loss is much the same. So this may seem big and scary, like a lot of new reactions, but it really is a minor difference, variation on a theme between otherwise mechanistically similar reactions. So that brings us to bromination and chlorination of benzene. This is a sort of a old school organic chemistry reaction. It works quite well. And common conditions for this, you'll see molecular bromine. When I say molecular bromine, I mean Br2, and a Lewis acid like iron tribromide. You'll often see many Lewis acids are things like transition metals or things like aluminum. And so what these do is they activate our halogen species to be a stronger electrophile. So our halogen species looks something like this. If we draw our Lewis structure, we'll see that there's lone pairs on our bromines. Each has 6 respectively. And what happens is our iron tribromide acts as an electrophile. And remember, the arrow starts at our electrons. So when our electrophile is activating our bromine, we get an arrow that looks like this. And what happens is our iron is a Lewis acid. It's kind of pulling electron density away from our bromine. And we could draw it something like this. You'll see different representations of this in the literature. But basically, the key feature here is that the iron withdraws electrons from the bromine. When you withdraw electrons from something, you make it more electrophilic. If you take them away, it wants more electrons from something else. And that is what the iron is doing in this case. It is interacting with the bromine in such a way as to pull electrons away from it. And when it pulls electrons away from it, it makes it much more likely that our benzene will act as a nucleophile with it. Our benzene is not a strong nucleophile. It only reacts with highly electrophilic atoms. And it gets us to the de-aromatized intermediate. And this is why we need such strong electrophiles. So this is no longer aromatic, and it has lost that aromatic stabilization energy. I'll draw my iron tetrabromide like this. You'll see different versions of how this is drawn. But basically what we're going to go with in this class is it acts as a base, and those electrons fall down to fill that carbocation vacancy. And what this results in is our side products, HBr plus FeBr3. You'll note that our iron tribromide was regenerated in this case. When bromine is protonated, it doesn't want to interact with the iron. And so we get our iron tribromide out. This is formally a catalyst, but we often use many equivalents of it. Okay? And so this reaction also works with iron trichloride and chlorine. So you can do the exact same reaction. It also works. I'll draw it below in a different color. However, this reaction is done a little bit less frequently because chlorine gas is so toxic. Bromine is something that can be handled in the lab setting, Chlorine gas is a little bit more frequently reserved for industrial settings at large factories where they can control it a little bit better. All right, so again, just to recap, this is very similar to our Friedel-Crafts reaction. We have an activation step. All right, we have attack, where our electrophile, E+, reacts with our nucleophile. Benzene is the nucleophile. And then we have the deprotonation, or proton loss. All right, so proton loss and rearomatization. This is the same exact sequence of events with slightly different reagents as our Friedel-Crafts reaction. So let's move on to another example that's mechanistically closely related, and that is the nitration of benzene. This is an industrially important reaction to generate nitroarenes. And again, it occurs through the same mechanism. However, the activation should look familiar for another reason. Remember in diazotization, we took nitrite, this molecule here, nitrite, and we activated it using protons, 2 consecutive protons to generate an NO+. Well, this reaction up here starts with HNO3. This is not nitrite. It's nitrate. But the general concept is the same. We activate our nitric acid, which looks like this. This is our Lewis structure. We activate it with a proton, and we protonate the OH group to generate the key electrophile. Draw going up like this. And that key electrophile, after loss of water, is called the nitronium ion. It is an extreme electrophile. We have a formal N plus water. Okay. So our water leaves, and this generates our strong electrophile, E+, that can then react with our nucleophile. We'll zoom out so we can sort of get the bigger picture. And again, this we did activate and then we did attack. And then we do proton loss rearomatization. We could use essentially a variety of things in solution. The one that makes the most sense here is to use water. Water is absolutely a strong enough base to deprotonate our dearomatized intermediate. And again, we'll call this proton loss. And aromatization. And rearomatization. That's what we called it before. One thing I'd like to highlight here is that you may wonder why we protonated this OH over here instead of the O- to activate it. Well, the reason is that we need a water leaving group. Water is a great leaving group. And if we protonated the other OH, we wouldn't really get anywhere. So in solution, we very likely protonate the O-. However, it doesn't result in loss. These reactions are often highly reversible. So we protonate the OH because it results in water, which we need to leave as have leave as the leaving group. So that's a little bit of a point of confusion, understandably. However, these reactions are reversible, and eventually we'll protonate the OH, and that can leave as water, and that results in our electrophile, the nitronium ion, which then attacks our benzene, which is then re-aromatized to 4-nitrobenzene. So let's think about the selectivity of this reaction. We can generate two products if we have a substituted benzene. When we have something just like regular benzene, all the CH bonds are the same. So nitrating them makes, which one we choose to nitrate makes no difference. But if we have a substituent off of our benzene, we now have to think about where the reaction is going to occur. So there's ortho, there's meta, and there's para. All three of these positions are, at least at face value, reasonable to react with. So let's think about what resonance tells us about the electron density of these reactions, or the electron distribution of anisole. And so if we take anisole, we can generate a resonance structure in which there is a anion on the ortho position. That resonance structure looks something like this. What this resonance structure says, again, oxygen like this is a pi donor. It doesn't say that there's an actual anion there. What it's telling us is that the way the electrons kind of slosh in the molecule on average puts a little bit more than we would expect at this position. But these electrons can also be resonated down onto the para position, and that gives us a second resonance structure where there's an anion at the para position. Remember that the arines in electrophilic aromatic substitutions, they are the nucleophile. And so where they have the greatest regions of electron density is where they're going to react with electrophiles. So we'll put our N next to them, nucleophiles, and our electrophile in these nitration reactions is the NO2, the nitronium ion. And what that ends up resulting in after re-aromatization, which I'm not drawing here, again, I'm not drawing the re-aromatization. That's what the second arrow means. I'm just, in the interest of time, since we've already gone over the mechanism, these are the two products we get. And they occur in about a 45 to 55% ratio. And you may say, why is the para product slightly more favored? Well, the anisole occupies some space. This is called sterics. And so there's a little bit of a steric clash between the nitronium and the OCH3. So the para position is just a little bit more accessible to the reacting species. And so the two main products that we get, and this reaction is actually quite selective for these over the meta, are the para substituted and the ortho substituted products.